Hey everybody, it's Mr. Mott. What we're going to do is go through titration calculations. We're going to compare how strong and weak acids react with strong bases. So we're going to be looking at prior to titration first, and we'll do the sodium hydroxide with our HCl, hydrochloric acid, first. All right. Prior to titration, just kind of think about what do we have in our burette and what do we have in our beaker. All right, so based upon how it's written, our sodium hydroxide is our titrant. It's in our burette. And then in our beaker, we have our hydrochloric acid, and this is 0.1 molar. And so our pH meter is in our beaker with the hydrochloric acid. And since hydrochloric acid is a strong acid, it fully dissociates. So to find the pH, we just need to take the negative log of our concentration, and so then our pH is going to be equal to 1. Okay. In contrast, when we look at prior to titration with our weak acid, our acetic acid, weak acids don't fully dissociate, and so we need to look at an equilibrium system, and so we need to make a ice table or even a rice table. All right, so we would have our acetic acid. We can draw it interacting with water. We're going to make H3O plus. This is, and then we have our C2H3O2 minus, our conjugate base over there. As far as our initial concentration, it is a 0.1 molar solution. Water we ignore. We don't have any of these to begin with. We are given the Ka here. We are given the Ka, so we know our change is going to be x. So stoichiometrically minus x plus x plus x, 0.1 minus x, and x. Now, one of the things that we've discussed in the past is that when you have a Ka value that's very small, like we do here, the extent to which the concentration is actually changing here in our ice table, very, very small. And so mathematically, we can ignore it. So when we set up our Ka expression, we have 1.8 times 10 to the minus 5, which is our given Ka. Product side, we have x times x, so that's x squared. And then in the denominator, we're going to have 0.1. And again, we're choosing to ignore the minus x here. And mathematically, it works out to be the same. When we then solve for x, x is going to be equal to 0.0013. And so remembering what x stands for, x in our table is our hydronium ion here, so we can take the negative log of that to find the pH. So pH is going to be equal to the negative log of our 0.0013. And so then our pH is equal to 2.87. All right. So kind of comparing and contrasting what our initial pHs would be on our pH scale. If it's a strong acid at 0.1 molar, pH of 1. If it was, in this case, a weak acid, it's going to be higher than 1. Depends on what your Ka value is to know, but it'll definitely be higher than, if it was 0.1 molar, your pH would be higher than 1, which is what we see here. All right. Next, we're going to be looking at, on the left-hand side, what if we have added 5 milliliters of sodium hydroxide to our hydrochloric acid. And so what we want to think about is that in titrations, when we want to think about what's happening, we want to pay attention to moles. All right, so we want to calculate our moles of NaOH and our moles of HCl. So for our moles, we're going to take our molarity, 0.1 molar, times our volume in liters, so 0.005 liters. And so for our NaOH, we get 0.0005 moles of NaOH. And for our HCl, which is what's in our beaker. Both are 0.1 molar, but we have 10 milliliters in there, so 0.010 liters. So we have 0.0010 moles of HCl. Now, in chemistry, you always like to really focus on the reaction. So in our chemical reaction, we have sodium hydroxide reacting with hydrochloric acid. And when that acid and base react, we call that neutralization. And we always make water with it, and we always make a salt. And it's important to recognize what type of salt that you make. All right. First of all, let's keep track of our moles. Our sodium hydroxide was 0.0005, and our hydrochloric acid was 0.0010. Okay. Now, when these reacting in a 1-to-1 ratio stoichiometrically. So our smaller amount is our hydroxide, and then all of that is going to react with the acid, and we want to figure out how much acid we have left over. So we're going to subtract out our moles of our hydroxide, and we're going to have 0.0005 moles of our HCl left over. The water we don't care about, but we also want to think about, we don't care about it in terms of it doesn't affect the pH, but what about NaCl? And what you remember from hydrolysis is that this is a neutral salt. This is a neutral salt. And so that we don't have to worry about because it's not affecting the pH. All right. So going back to what do we have left, we can figure out our concentration of our HCl, and we have 0.0005 moles of HCl. And what we want to think about is what do we have in our beaker. We had our original 10 milliliters plus the 5 milliliters now, so our total volume is 15 milliliters, or 0.015 liters. And so our concentration then is 0.033 molar, and then we can take the negative log of that to find our pH. Oops. And so when we take the negative log of that, we get around 1.48. And so if we can kind of compare on the strong acid side, we start out with a pH of 1, and then we're halfway to the equivalence point, and we have a pH of just a little bit more than that. And so really only the pH is really changed because of the added volume, and then a slight decrease in the moles, but the moles that we have left over are moles of a strong acid. So our pH is still really, really low. All right. Let's take a look on the acetic acid side. Now, one nice thing about all these calculations we did, the number of moles is actually the same as what we had before. So let's go ahead and write our reaction then. Our reaction between these is NaOH reacting with our acetic acid. And we're going to make, and this is our neutralization, we're going to be making water, and then we're going to be making our sodium acetate. Sometimes we just write this as the acetate ion. What's important about this is that you'll notice we have our weak acid, and we're making a conjugate base. And that's going to be really, really important here, that we're making something that isn't neutral. All right, let's take a look at our numbers. Even though we are dealing with a weak acid here, the amount of moles that we have to start out with is the same, because our molarity and our volume is the same. And our moles of base are the same because we've added that the same as well. All right. So when we think about our moles, we had 0.0005 moles of NaOH, we had 0.0010 moles of our acid, and our base is the smaller amount, so that's going to get completely used up. So that's going to be gone. And then some of our weak acid is going to get used up, 0.0005 moles. And we have 0.0005 moles of our acid left over, our weak acid left over. The water isn't playing a factor in equilibrium, it's not changing the pH. We didn't have any of our conjugate base to begin with, but when the acid and base reacted, we made our conjugate base. And we keep track of it because conjugate bases are impacting our pH. So we have an increase of 0.0005 moles. So we're a total of 0.0005 moles. And so what we have left over, so this is our neutralization, which is our step one. Then we think about equilibrium because we've made a conjugate base and we have a weak acid. And so what we have here is that we have a weak acid and its conjugate base all in there with water, and this is known as a buffer. And when you have an acid with a conjugate base, that's a buffer system. And buffers work to keep the pH from changing very much. All right, so now what we need to do is write an equation that has both of these in here. And I'm going to write this from the perspective of the acetic acid because we have the Ka of acetic acid. All right. So our equation is going to be our acetic acid interacting with water. We're going to make some H3O plus, and then we're going to have our conjugate base here. And we're going to plug in our values from what we have. So again, from our calculations on the left-hand side there, we have the same number of moles that we have from the hydrochloric acid in the same volume. So we have 0.0005 moles of it, and we have the same volume like we did over here. So the concentration of our acetic acid is 0.00 or 0.33 molar, just like on the left-hand side. So this concentration is from our initial concentration is 0.033. Our moles of our conjugate base are the same, and the volume is the same, so our concentration of this is the same as well. All right. Water, again, we ignore. We didn't have any of this to begin with. So since I'm writing this from the perspective of the acetic acid, my change is a minus x. This is plus x, 0.033 minus x. We have x, and then we have 0.033 plus x. All right. Now, when we write our Ka expression here, then same sort of idea as before, we are going to be ignoring the change in x, because again, our Ka expression is our Ka constant is very, very small. So our concentration of the weak acid and the conjugate base, they don't change very much. So I'm going to have my 1.8 times 10 to the minus 5, which is my Ka. On the product side, I've got x, and I've got 0.033, again ignoring the change in x. On the left-hand side here, or the my reactant side, 0.033 as well. So you can tell that our 0.033s, they cancel each other out. X equals 1.8 times 10 to the minus 5. That our x value tells us our pH. So by taking the negative log of our 1.8 times 10 to the minus 5, we should get our pH. So our pH, when we do that calculation, is going to be 4.74. And what you'll notice is that we're taking the negative log of the Ka, right? And so not only does it tell us our pH, but the pH is also our pKa. And this is the case when you are halfway to the equivalence point. Okay? Now, the equivalence point, if we back up a little bit, we want to remember what we had initially in our flask. Okay, so like initially in our flask, we had 10 milliliters of a 0.1 molar acetic acid solution. Okay, writing this near the top of the screen. And so we have the same concentration of base as we do our acetic acid, and we now have added half the volume, so that's half the number of moles, so we are halfway to the equivalence point. And again, this idea down here at the bottom, that halfway to the equivalence point, the pH is equal to the pKa, that's a really, really important idea. All right. Let's continue on in a second video.